even out, and there you'll see exponential decay. On the flip side, let's say you put a meatloaf in an oven, right? And when you first put the meatloaf, the raw meatloaf in the oven, it's probably room temperature, right? And then it's going to increase quickly at first, and then it's going to even out, right? And when it evens out, it's going to even out to what temperature? Whatever temperature the oven is. So if you set the oven at 400, 400. This kind of temperature that it evens out at, I don't really see this word come up a lot, and that clearly didn't show. It's called the ambient temperature. It's the temperature of whatever's surrounding the object, right? It's either warming up to that temperature or it's cooling down to that temperature. So that's the ambient temperature. So that's just really the gist of what we're doing, and based on like the shape of that, you can see that it cools quicker and it heats up faster as soon as it gets in. The reason for that is because that's when the two temperatures of the two different things are most extremely different, right? And if they're the more extremely different they are, the quicker they'll initially come together, and then as they get closer together, the speed of the cooling or the heating won't be as much. All right, so this first example, I don't believe even talks about law of cooling, but we're given an exponential function. We know it's exponential decay, right, because it's less than 1. It's decaying by 50%. Starting value is 8. It says use your calculator to sketch the graph. I don't think we necessarily need that, but we should know it's starting at 8. And after every minute, it becomes half of the amount. So if I do 1, 2, 3, 4, 5, after 1 minute, it's 4. After another minute, it'll be down to 2. After another minute, it will be down to 1. After another minute, it'll be down to a half, and then down to a quarter. So here's the first 5 units of what's happening. Clearly the value of y is getting smaller as x gets larger. Does it ever reach 0? And that answer is no, because we keep multiplying by a half. Because we keep multiplying by a half. And the only way it would reach 0 would be if we multiplied by 0. I'm just going to leave it at that. Okay, so it kind of is, it's getting at that idea that it's always going to be decreasing, but not enough to ever cross 0. And that, in this particular case, 0 would be like the ambient temperature, or the ambient value that it's getting closer and closer to without ever actually reaching. Okay, because people could even argue that that cup of coffee that we put on the counter never actually reaches 70 degrees. If the room temperature is 70 degrees, the coffee is always going to be at like 70.000000001 or something like that. I think technically that's not true, but when you visually show something on a graph, you don't actually ever reach that ambient temperature. But you get so close that it's essentially the same thing. So here we have a liquid starting at a temperature of 200, and it begins to cool in a room that is a steady temperature of 70. So draw a rough sketch of what this would look like. So if I call this 200 just because that's the one that's labeled, then that means 100-ish is here, which means 70-ish is right there. And I want that. That's like a horizontal asymptote, because I'm starting at 200 and I'm exponentially decreasing to 70 degrees. So part B asks you, why would this equation not work? This is an exponential parent graph. Exponential parent graphs have asymptotes on the x-axis. So that's why that exact format wouldn't work for this one. But if I just shifted this parent graph up 70 units, now it would work. If it was A, the initial temperature, B, the growth or decay factor to the T power, and then there was a plus 70 or a plus D, something like that, that shows that this whole thing got shifted up however many units to whatever the ambient temperature is, then it would work. So that's what we're getting at. How could we modify this equation to make it model the situation? That would be like y equals A times B to the T, but like plus some C value, where C would stand for the vertical shift. C would stand for the ambient temperature. Is it 1,000 degrees in here again? No? I'm hotter today than I was yesterday. If anyone wants to crack a window, you're welcome. I wonder if the science people are done having so much fun we could open the door again. All right, so after sitting out of a refrigerator for a while, this is a totally new question. This is not that hot cup of liquid. New question. After sitting out of the refrigerator for a while, a turkey at room temperature 68 is placed into an oven at 8 a.m. when the oven temperature is 325. So right away, I'm just going to give myself a visual. An oven temperature is 325. Sounds like the math people are having fun now. How do we get that, math teacher? All right. The pencil's being difficult. This turkey starts at 68, which is probably something like that. I'm just totally sketching. And it's going to increase up to 325, essentially. We're putting it in at 8 a.m., so this is at 8 a.m. Newton's law of heating explains that the temperature of the turkey will increase proportionally to the difference between the temperature of the turkey and the temperature of the oven. That's a lot of word. As given by this formula. I think this might have actually been on a Regents. They give you the formula, and I think I cut it out, but they did actually give what each of those variables stands for. The capital T stands for the final temperature of the turkey. So write that down for capital T while I look for more lead. What do you think T sub A stands for? The what? Not initial. That's what T sub 0 is, though. Who said something, Chris? Nope. Capital T is the final. T sub 0 is the initial. T equals final temp. T sub 0 equals initial temp. Any guesses? T sub A? Nobody? Jack. The ambient, exactly. The ambient temperature. So that covers T, T sub A, T sub 0, T sub A again. E isn't a variable, it's a number. K is kind of like your rate. Almost like the PERT formula. Does everyone see how that's sort of playing like e to the RT power? And T is your time. The amount of time that this is lowercase t. Lowercase t is the amount of time this is spent in the oven. So, what do we already know before we read the next paragraph? We know the initial temperature. What's that? 68. We know the ambient temperature. What's that? 325. That's the temperature of the air surrounding the turkey while it's in the oven, 325. So then this next section is going to give us more information, because right now we only have 2 of the 5 variables. The turkey reaches a temperature of approximately 100 degrees after 2 hours. Where will that 100 go, Vince, and where will the 2 go? Yep. And 2 for time. Perfect. So now we have 4 of the 5 variables. Which variable don't we have, Elena? We had 68, 325. Vince just told us that 100 degrees will be the final. After 2 hours will be the time. K. We don't have K, so that's why they're asking for it. We're going to find K. So plug in our final temperature. T is 100. Ambient temperature is 325. Plus T sub 0 is 68. Minus 325. E to the negative K times a T value of 2 hours. Now, we're going to solve for K. And K is really going to be a constant that is wrapped up with the rate at which this turkey is increasing. Okay, it's almost like the rate from your PERT formula. Before we get started, we're going to subtract this 325 over, which gives us negative 225 equals this 68 minus 325 that's in parentheses. I'm going to do that subtraction and simplify those parentheses first. That's negative 257 e to the negative 2k power. Natalie, what would I have to do next to solve this? Not ready for that yet. You can't take the natural log until the exponential part is by itself. Yes, divide the negative 257, which is probably going to give us a nasty little decimal, so I'm just going to keep it 225 over 257. You notice I did take care of the double negative in my head. I just figured double negatives don't matter, so I'll just get rid of that. Now I'm ready to do the natural log of both sides. So I'll natural log the left and natural log the right, which will technically take that e out of the picture. And Jack B, last step. I'm solving for what? K, and what's still with the K that I have to get rid of? How do I get rid of the negative 2? If the natural log of this equals negative 2K, how do I get K all by itself? Divide by negative 2. Technically, it's already out of the exponent, right? So divide by negative 2, divide by negative 2. So K equals, and it says to round the nearest thousandth. This is another big reason why I don't do 225 divided by 257 too early. Because if I do that division, make it a decimal, I'm going to have to round that decimal, and then when I take the natural log of a rounded answer, it's going to throw it off. So we keep it exact. We do the natural log of 225 divided by 257, and take that answer and divide it by negative 2. And it says to round to the nearest thousandth, which would be 0.066. So that now goes back up here, and that rate is going to be consistent for the rest of the problem, 0.066. The amount of time that's in the oven, that can still vary, and the final temperature can vary. They just gave me that one circumstance that allowed me to find the constant rate. Now that I have that constant rate, I can use this to figure out the temperature of the turkey after 5 hours, 7 hours. When will the turkey reach 300 degrees? I could be asked kind of this in any any given way, but these three numbers are the same throughout the entire problem. The only things that can change are the amount of time the turkey's in the oven and what final temperature the turkey actually gets to. Does that make sense? So the follow-up with this is determine the Fahrenheit temperature of the turkey. So we're looking for capital T to the nearest degree at 3 p.m. What do I plug in for little t, the time, at 3 p.m.? Chris? 7. And explain to everybody how you got 7. Right. So don't make the mistake of plugging in 3 for little t, because it's not staying in for 3 hours. You're putting it at 8 a.m., you're taking it out at 3 p.m. That's actually 7 hours of being in the oven. So little t equals 7. And then I have capital T equals, the ambient was 325, plus parentheses 68 minus 325. I'm just plugging in everything I know. E to the negative, K is 0.066 times 7. And this isn't really a solving question, because capital T is already by itself. This is just plug that in verbatim into your calculator. So 325 plus parentheses 68 minus 325. Close your parentheses. Multiply it by E raised to the negative 0.066 times 7 power. Final temperature of the turkey, if it's only in for 7 hours, is what'd you get, Jason? Yep, nearest degree, 163 degrees. So it's not even close to having reached the temperature of the oven yet, the 325. But I'm pretty sure turkey is done. Like if you Googled it, not that any of you are cooks. I'm curious. Oh, my computer's not even on this little day. 175 maybe, 170, 160. Oh, poultry's 165. Look at this. How do you know that? You do? That's amazing. I'm gonna see what you're cooking over there. You could bring in a meal for us. Okay, so poultry's 165. That was easy. Lucas is our real life Google. Okay. Okay, we're not going to do out everything. I'm going to go somewhat fast through this, but we're sticking with the same cooling liquid that we had before. So think about that cup of coffee we put on the counter. One that starts at 200, cools down in a room that's a constant temperature of 70. We will now model this cooling Fahrenheit temperature using this equation where A, B, and C are all parameters in the model, and T is the time in minutes. So which of these constants equals the 70? Quick. Which one's the room temperature? No. A is the starting temperature. C, that's the shift up that we did, right? So C equals 70. A is the starting temperature, that's 200. And B is our kind of our growth, I guess we're cooling, so it's our shrinking rate. It's going to be something under 1, I would assume. But we don't know that yet. Oh, I lied. A's not 200. I'll tell you why in a minute. Don't worry about that. I take it all back. I said something wrong. None of these constants is equal to 200. You know what A is actually equal to? A would have been 200, but this whole graph got shifted up 70, right? So it's going to be 270. We'll get there. This is going to kind of talk us through that process. So if we go to our, what they just tell us, they tell us at the 0 minute mark it's 200. So if we plug in a T of 0 and a final temperature of 200, we get 200 equals A times B to the 0 power plus 70. This is what's going to tell us what A is. Nope, I did it backwards. I went the wrong way. So you plug in 200 for your final temperature, you plug in 0 for your number of minutes, you don't know A or B yet, and you're shifting it up 70. And so when you solve this and you subtract 70 from both sides, you get 130 equals A times B to the 0 power. B to the 0 power is just 1, right? So A was 130. Do you see how we went the wrong way? We went 70 above 200. We should have gone 70 below. So we wanted this temperature to start at 200, and we did this on the front, and it cools down to 70. So if we were to back this up, and now you'll see it more clearly why it's 130. If we were to back this up and shift it back down 70, do you see why your y-intercept is 130? Okay, does that visually make sense? In order to find the value of B, we're going to need an additional time and temperature. So that's where part D comes in. So we know that A is 130. And in this one, they're giving us a final time and a temperature. So it's 153 degrees. A is 130. B we're looking for. That 153 degree temperature happened after 5 minutes, so our time is 5 minutes. And our C was 70. We have to subtract 70 from both sides first. 153 minus 70 is 83. Divide both sides by 130. How do we get rid of the fifth power? You raise it to the reciprocal. Very good. Raise to the 1/5. Raise to the 1/5, and we find out that B equals, and I'll just do this on my calculator quickly. Hold on, 0.91. So your final formula is 130.91 to the T plus 70. So growth or decay, and by what percentage? 9%, right? 0.91, 9%.
But I'm coming.